Okay, so these are going to be the notes for 1.1 if you miss class or you have some questions about the homework and how you should go about it. So we're just going to fill this in as we go and try to help make sure that you have everything that you need. First thing you need to understand is that physics studies phenomena or phenomenon, but phenomena because it's plural, that can be observed with our five senses. When we talk about a model that we use in physics, we're talking about some sort of a representation. Okay, so you're thinking about a representation that is a good model or good, well, again, representation of something that maybe we can't explain as simply, or it isn't as easy to understand. So an example would be a model of the solar system or a model of the universe. We use these to model or to show what we have a difficult time explaining with just pure math. And so we use these models to make them easier to understand and interpret. A theory, you know, it's a little bit more than a hypothesis. It must be backed by evidence. Okay? So you're going to ask, do I have evidence of my theory? Has it been modeled? Can it be modeled? It is, at the end of the day, while it's widely accepted, it is not a guaranteed law. It's not fully proven. There's a lot of evidence and tests, but not proof. Not what we would put on the level of proven. Okay? A law, however, it's going to use specific language, okay, to describe general patterns, and that have often been verified many times. Okay, we're not going to accept a one-time, hey, look, see, I proved it, it must be a law. These need to be things that we have seen several times. Okay, so when we get into the scientific method, typically we're going to begin with observations. And questions about the phenomena to be studied. Next, we're going to preliminary research is done, and the hypothesis is developed. Okay, so we're going to come up with a hypothesis. Then we're going to then experiments are performed to test the hypothesis. We need to know, is it right or is it wrong? And finally, we analyze those tests and we come up with a conclusion. Now, there's obviously sub-steps or other parts to the scientific method, but this is at the heart of it. Okay, science uses in our classrooms, we're going to use the international system. Now, you might wonder why it's called, you know, SI if it's international system. But you have to remember that aside from English, this would probably be pronounced, you know, system of national. If you think about French or Spanish or other languages, our language in English is written a little bit differently. Our base units that we use for the international system would be length, would be measured in meters. Then time would be measured in seconds. Mass is measured in kilograms. And you can see those units off to the side. Over here, you can see all of these prefixes. You know, we obviously have our kilo or kilometer or kilogram. That makes it 10 to the third or 1,000 of a regular unit. We also have things like nano. You might think of a nanometer being really tiny, 10 to the negative ninth, and so on. You can keep track of that. Other units are composite. Okay, what that means is that we can create them using the units that we already have. All right, let's go ahead and slide down a little bit. So some of the things that we need to do is we need to make some basic conversions. Okay, and so we can notice this big G here, which is convert 20 giga, okay, that's 10 to the ninth, gigameters to regular meters. Converting 5 centigrams to kilograms, and then converting kilometers per hour to meters per second. Those are conversions we want to be able to do. And so as we go through when we go through and do an example problem here, let's grab maybe a different color this time. Let's grab our green. Let's do this conversion. As we convert 20 giga, and that would be 10 to the 9th. So this would be 20 times 10 to the 9th. That giga is represented by the 10 to the 9th, which means that now I'm in meters. So these straight movements are pretty straightforward when we're going to the standard unit of meter or gram. It's a pretty straightforward switch there. So literally, this would be 20, comma, 1, 2, 3, 4, 5, 6, 7, 8, 9 meters. Or the way we prefer to write numbers this large is 2.0 times 10 to the, would be 9/10 meters. Okay, now those numbers are so big that it's just nice to have something else. And when we move centigrams to kilograms, we have to realize we can make this really simple. If we look at the centigram, it's 10 to the negative 2. So we have 5 times 10 to the negative 2, okay? And we want to turn that into kilograms. Okay, so this is in grams now, because that 10 to the negative 2 is the centi. So now I want to turn that into kilograms. Well, to convert something into kilograms, it has to be 10 to the 3rd. So the question is, how do I make that a positive 3? Well, because it's a negative 2, I would have to add 5 to it, right? Add 5 to negative 2, you're going to get positive 3. Adding 5 to that exponent, okay, means that I'm going to have to move the decimal over here. Sorry, it starts out right here. I'm going to have to move it left to compensate for the bigger exponent. So as I move it left 5 times, I end up with 0.00005 kilograms. Now you might ask, are we sure that that's right? Well, if I move it 3 to grams, that would be right there. Okay, that would be from kilograms to grams, and then if I move it 2 more, that would put me at centigrams. So 0.00005 kilograms. This last one is actually where we do a lot more of this type of stuff all the time. 25 kilometers per hour, and I need to convert it to meters per second. So the way that I'm going to do that is by putting my kilometers down here and meters up here, so that my kilometers will cancel. But I can't do that without the numbers that go with it. Well, 1 kilometer is 1,000 meters. So now that conversion can take place. And then I have to convert my hours. And so I have hours and I want to get seconds. Well, 1 hour is 3,600 seconds. And so we can see how the hours are going to cancel. In this problem, I'm going to take 2,500 times the 1,000, and then I'll divide it by 3,600. Let's see if we can do that real quick here. If I get my calculator to turn on. There we go. So I'm taking 25 times 1,000, and I'm dividing it by 3,600, and I get 6.94 meters per second. Okay. As we keep going through looking for more information, we're going to talk about accuracy for precision versus precision. And so as we look at our accuracy versus precision, okay, accuracy is how blank a measurement is to the blank valued statement. So that is how close it is to the correct value. We want to be accurate because we want the right answer, and we want to be as close to the right answer as possible. However, precision refers to in the system refers to how close the agreement is between different measurements. In other words, if I take the same measurement multiple times, will I get the same thing? that right there is precise. So we'll put a P there. And this right here, because they're all close to this middle value, this is an example of accuracy. What we really want is both. So accuracy and precision mean that there is some error. There's going to be error. A device that can repeatedly get the same answer, but so it can get the same answer, be precise, but not always be correct. I mean, if you think about a real life scenario, maybe you're measuring tape, it's not written on right. You always get the same number when you measure a piece of wood, but they're not the right measurement. That wouldn't be a perfect system. And so we got to realize that accuracy and precision both matter. So we use significant figures to reflect, error. We know that there's error in measurements, and so we want to acknowledge that. So then each measuring device can only measure so accurately. The leading digit is always a sig fig. I'm not totally sure what that worksheet meant with that, but anyway, our leading digit that's non-zero digit is going to be a sig fig. To find more significant figures, we ignore place holding. Zeros between a decimal point and the first non-digit, and then we count the other number of other digits. Okay. So a couple of quick examples. This is an example where there's only 3 sig figs because all these zeros over here don't matter. Here, this is a little bit of a misleading problem. It looks and it should be 4, but we don't actually know. Because they're not leading zeros, they're not between, they could be accurate, they could possibly not be. We'll go ahead and say 4 with some uncertainty in those 3 digits. And then here, of course, we have 4 because we go from the 1 through the 3. There's 4 digits there. When it comes to adding and subtracting, okay, the answer, okay, can contain no more decimal places than, let me go back to there, than the least precise measurement. So in this case, here's my least precise measurement. It doesn't have as many decimal places, so I have to cut off at that point, which means I can't really look at that 2, 3 at the end. If I add these, I get 3.04. Now, a lot of times it doesn't actually matter because it's not like that 2 was going to round the 4, but we do have to deal with just the numbers we have. When it's multiplication, you have to have the same number of decimal places. As the quantity having the least significant figures into the calculation. So right here, this goes out to the 3rd decimal place. So when I do this multiplication, that 3 is going to drop. I can't go that far out. And so if you went through and made this calculation real quickly, I'm not going to be able to see it all. So we've got 1.002 times 2.0223. I'm going to do the multiplication with the whole problem, but now I'm going to have to cut it off at the 3rd decimal place, which would be 2.026. 2.026. All right. Go in and take care of the assignment that you see down below. Hopefully you have that from class, and we'll talk about it more. Bring your questions. If you have any questions about the video, just let me know, and I'll see you in class.